Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimize the total price of the trips. The problem is quite interesting. In this particular video, we'll be discussing about two different versions of the problem. If you have solved it already, you can skip to the particular section of the video. All the timestamps would be there in the description down below. With that, let's get started. The problem states that you are given a unrated, unrooted tree with n nodes, and you are given all the edges of the tree. Each node of the tree has an associated price, and for each node you are given the price array which denotes the price of the ith node. The price sum of a given path is the sum of prices of all the nodes lying in that path. So let's say you have to find out the price sum of path starting from 0 and ending at 3. So in that case, the price sum would be the sum of all the nodes, sum of price of all the nodes which are lying in the path from 0 to 3. So 0 to 3 has 3 nodes, 0, 1 and 3. The sum of all the nodes would be 1 plus 2 plus 3. So price sum of this path would be 6, right? So you are given some trips. Each trip is described by start index and an end index. Basically, you will start the trip at start index and you will end the trip at this particular end node. Now, you have to return the minimum total price to perform all the given trips, right? So you might be thinking that why it is minimum, because if the entire we are given a tree and there's only one path between two nodes, right? So the sum of all the path price sum would be constant. So here comes the twist. They are saying that you can choose some non-adjacent nodes and halve the price. So you have to choose this adjacent node optimally such that the final price sum is minimum possible, right? So let's take an example. Let's say this is the tree, right? And we have given these three trips. First trips from 0 to 3, that is you'll start at 0 and end at 3. Second trip from 2 to 1 and so on and so forth, right? Now, as it is given in the problem that you can half the price of any node which are non-adjacents, right? So let's say we have the price of this node and this node. So this node, the price was 10, so we have it to 5. Price was 2 here, we have it to 1. Price was 6 here, we have it to 3, right? Now notice that we are able to do so because this 2, 0 and 3 are not adjacent. So we can't actually half the price of 1 because 2 is already halved, right? So this is, let's say, our final tree. Now from 0 to 3, what is the path sum? 0 to 3 path sum would be 1 plus 2 plus 3, 6, right? Similarly, from 2 to 1, what is the path sum or price sum? This 2 plus 1, sorry, 2 to 1, right? So 2 plus 5, 7, right? And similarly, from 2 to 3, it would be 10. So total price sum would be 6 plus 7 plus 10, which is 23. Now you can try any other possible combination of making the nodes or making the price halves. You will see that you can't achieve a total price sum of less than 23, and hence 23 is our answer, right? So hope the problem statement is clear. Now, as always, let's try to reduce the problem first. Let's say there is no concept of reducing the price to half. So the problem states that you are given some trips, you are given a tree with n nodes, you are given some trips, you just need to find out the price sum for all the trips, right? So again, I would be I would be explaining this part for beginners as well. So if you're already aware of this particular section, all the timestamps are there in the description down below. You can move back and forth in the specific sections. So we are trying to solve the reduced problem first. That is, we know that every price of every node is constant and that will not change. We just need to return the price sum for every trip that is given to us, right? So these are the trips that are given to us. We need to find the price sum for each of these trips. Now, what exactly we need to find? So let's say for 8 to 9. So 8 is this, right? And 9 is this. So we have to figure out the nodes that lies in the path from 8 to 9, right? So that's the first thing we need to figure out. If we are able to figure out this, we can simply sum up their values, and that would be the price sum for this particular trip. And we can repeat the same for all other trips and we'll get the answer, right? Now, what is our problem now? The problem is now we have to find out the path between two nodes u and v, right? How to find path? Because it is a tree, every like the path from u to v is constant, and it can be broken down into two pieces, that is path from u to lca and path from v to lca, where lca is the lowest common ancestor. So you can see each path will actually meet somewhere in the top, right? So this is, let's say, the lowest ancestor where these path will meet. So the path from 8 to 9 can be broken into this path from this ancestor or 5 to 8, and then path from 5 to 9, right? So once you figure out 5, what you can simply do is just go up from 8 until you hit 5, and whatever nodes you will encounter, all those nodes would be part of your path. Similarly, you will apply the same process for the next node as well, like from 9 as well. You will go up, find 5, and all the nodes in that journey would be in the path from 9 to 8 or 8 to 9, right? So the next thing is how to figure out this lca. If you haven't like if you know how to find lca, you can skip to the next section, but let's see how to find lca. The smallest thing, or the quickest thing you can do is you can simply go up one by one from each of these nodes. So from 8 you go up one, from 6 you go up one, you will reach this and this, right? Now again from here you will go up one, and from here you will go up one, and finally you reach at the same node. So bec- because you reach at the same node, you know this completes the path. So basically this is the final path. So what you can simply do is start going up from each of the node until you hit a common node, and all the nodes in that journey would be in your path, right? So this works. But let's say the let's take about the second example, 2 or 2 comma 3, right? So in this case you can see 3 is this and 2 is this. If you apply the same trick here, let's say you started going up, you start going up from 3, you start going up from 2. So you can see you will never be able to meet at a particular position. So the parent of 3 would be 0, so you will come here, right? And similarly for from 2 you will come here. Now again you will move parent because they are not equal. So once you move up, you will hit 8, and from here you can't move up because there is no parent of 8, 0 at all. So basically you will hit null pointer exception or something of that sort. So basically this would not work in this scenario. Now what is different in the current scenario and the scenario that we have taken previously with 8 and 9? The difference is they both are not at the same level. If they, in the previous scenario where we have considered 8 and 9, 8 and 9 were at the same level. So we know both 8 and 9 have exactly same nodes above them, same number of nodes above them. But for 2 and 3, that's not the case. So that's where the first job is to make the level same. So let's take this example 1 and 3. So 1 is this, right? And 3 is this. So we know the level of 3 is 2 and level of 1 is 3. So what you will simply do, you will first bring the higher level to a common lower level. So you will say that, okay, I will first bring this 1 to 5. Basically the difference is 1, so you will move one time and you move up to this node. So once you reach here, now the level is same. Now you can apply the same trick. Just start going up until you hit a common node, and that all the nodes in that path in the journey would be the part of your path, right? So hope you get this entire algorithm. Just to reiterate what we are doing, we are first making the levels same. So from every node, for two nodes, whichever node has the higher level, we just move that node to the level which was the value, the level to which the lower value belongs to. Once you make the level same, you will start going up one by one until you hit a common point, right? So how would the pseudocode look like? Pseudocode would look something like this. So as discussed, we will start by making sure that level of both of them are equal. So if level of both of them are not equal, we are assuming that u is the one which have lower, which have higher level always. If that's not the case, you can just swap u and v, and this condition will be satisfied, right? So because u has the higher level, we simply move u one up, right? And while moving up, we are also keeping track of what all nodes we have visited, because that all would also be part of your path from u to v, right? Now once the level is same, you will move one by one until the nodes are actually same, right? So now is the time to move one by one. So let's say in this particular case, you have reached 6 and 8. Now we'll start moving one position up at a time. So we will do this until we hit a common node. So while u not equals to v, we will simply push the current u into our result and update u, and push v into the result and update v. After this entire loop ends, we know u and v both are equal, and they are actually pointing to the LCA. Now notice that you have taken 6 and 8 into the result set, and 2 as well. But because this loop will end as soon as u and v will be same, you have to manually push u at the end. So it doesn't matter whether you push u or v, they both are same. So you can just push one of them. And finally, this result vector will contain all the nodes that will lie in the path from u to v, right? So hope this entire point makes sense. Now what we require to make this algorithm work, we require two things. First, we need to understand what is the parent of a particular node. So we have to build this array for where each index would denote what is the parent of that particular node. And second, we have to build this array as well, basically where each index would denote what is the level of that particular node, right? So building out parent and level is very straightforward. You can just simply apply a simple DFS and build both the array in a single shot, right? So what we can simply do a simple DFS starting from source to parent. Initially source, you can root the tree at any node, because the tree is unrooted. You can root the tree at any node. Let's say we root the tree at 0. For 0 we know that there is no parent, so we'll just mark -1. So we'll call this function with these arguments, and inside this function we will simply mark the parent of src as parent, and level of src as level of parent plus 1, right? And inside this do we iterate over all the child and then figure out the same thing for all its children as well, right? So just to dry run this, initially the level of parent is level of -1 is 0, right? So level of -1 is 0. So once you reach 0, you will say the level of 0 would be the level of parent plus 1. So level of parent was 0, so level of 4 would be 1. Similarly, for at this particular pace, level of 5 would be the level of 0 plus 1. So level of 0 was 1, so level of 5 would be 2. And sims in the same way you will fill everything. So with this algorithm we get level and parent, and once we have level and parent, you can simply apply this algorithm to get the path between two nodes u and v, right? Now what is like, once you get this path, you can simply sum up their values and for each of these strips, and you will get the answer. Now what is the time complexity? For first of all, we have to figure out the level and parent, and we are running this DFS. So this DFS would take order in time, right? So because we are visiting each node exactly once, so this DFS will take order in time. Now for each of this strip, you are doing something. For each of this strip, you are finding out the path. Now path can be like in worst case what can happen is the tree is a linked list, right? So every node is just children of the parent node, that's it. So in this particular case, the path between two node can be at max order of n, like there can be n nodes in the path, and hence this path function would take order and time in worst case. So order and time for each trip. Now there, let's say there are t number of trips. So this entire uh, algorithm would run into order n plus n into t time, where first n is due to the DFS and second n into t would be for each trip you are finding out the path that would require order and time. So this is the final time complexity of the current algorithm. Now notice that we haven't considered the actual problem. We haven't solved the actual problem yet. The actual problem states that we have to half the price of some non-adjacent node as well. We haven't considered that yet. But this solution would definitely work because n and t are small in this particular problem. So we have solved the reduced problem now. Now comes the next version wherein we have to actually solve or actually consider the case wherein we can halve the value of some nodes uh, before actually performing any trip, right? Now which one of these nodes will you have? So one thing you can do, okay, I have to have adjacent, I can't have adjacent nodes, so let's just pick all the non-adjacent levels and have them. So let's say you say that, okay, for first level you will have all the nodes in the first level, you will have all the nodes in the third level, and similarly you can have all the nodes in the fifth level and so on and so forth, right? This is the one possible choice, right? Second possible choice can be, okay, I can have the node of second level, I can have the node of fourth level, and so on and so forth. Now this particular greedy approach would not work. Why this would not work? I would strongly encourage you to pause the video and try to think of a counter example yourself. So what we have to find is an example wherein halving all the nodes at alternate levels would not give you optimal answer. Uh, I am again I would encourage you to pause the video because if you are able to find the counter case by yourself, you will get much better understanding of the underlying issue and the solution for that. So this is a sample scenario wherein this algorithm would not work. So let's see. So first 6 comma 6. So basically we are saying that this is the only node in this path. So we have to take 10. Now second is 9 comma 9. Again, this is the only node. So we have to take 8. Then 8 comma 8. Again, this is the only node, right? And then 7 comma 7. So this is the node, right? Now let's say you have the alternate levels. So let's say you first check, okay, what is the value if I have uh, odd levels for 1, 3, and 5, and so on. So in this case, the value would be 10 plus 8 plus 6 plus 2 because this one is half. So this one was 2, 2 plus 6, 8, 16, 26. The value is 26, right? Now let's say you say that, okay, I would instead of halving the odd levels, let's halve the even levels. Let's say you have all these things. So this 10 become 5, this 8 become 4, 5 plus 4 9, 6 become 3, 9 plus 3 12, and 12 plus 4 16. So now it comes 16. So you can just take the minimum of those two and you can say that this is the answer. But you can even have a answer less than 16 as well. How? Just half only these nodes. Now notice that you can have all of these nodes because all of these nodes are not adjacent, right? Again, in the previous scenario, where you have all of these nodes at the second level and all of these nodes at the fourth level, you can't actually have this 7 because this will be adjacent to one of these, right? But now what we're saying is we'll not have everything here. Instead, we'll just have these nodes, and we can see that we are able to achieve much better result here. So what is the value? What will be the value now? 5 plus 4 9 plus 3 12 plus 2 15. Sorry, 12 plus 2 14. So the value now is 14, which is better than both 26 and 16. So this is why the greedy approach of just halving odd or even levels would not work, right? So now what exactly will be the solution? So before going there, let's first try to just convert this tree into another tree first. So let's say we we have to find the path sum or minimum path sum, and we have the power to half the value of any node, right? So in this case, let's just try to find out the total nodes which are actually contributing to our result. So let's say from 8 to 9, what all are the nodes? These are the nodes, right, which are contributing to 8 to 9. Now for 2 to 3, what are the nodes? These are the nodes. Sorry, 2 to 3, right? So these are the nodes that are contributing 2 to 3. And from 1 to 3, what are the nodes? These are the nodes that would be contributing to 1 to 3, right? So let's just sum them all up and just forget about all other nodes completely. So basically, even though the value here is 10 and 8, we will not care about this 10 and 8 because these two are not getting considered in any of the trips, right? So let's just take the sum of each of these paths. So now 8 comes 1, 10 comes 0 times, so we replace this with 0. 8 comes once, so we have this 8. 0 comes once, so we have the 0. 6 comes once, so 6 is there. Now 2 comes twice, one is in this path and second in this path, so we just double this 2 to 4. Now 6 comes twice again, so this 6 is 12. 4 comes once, so 4. 8 comes twice in this path as well as in this path, so this would be 16. So just forget about 16. I think I made this mistake, but let's say this is 8 somehow. And now this comes twice, so again this 4 this comes once, so 4 is 4. 2 is 2, and now this doesn't come anytime, so this value of this node is 0. Now we have built this tree. Now what our motive is now? Motive is to actually figure out the sum of the maximum or the minimum sum possible if we half the node of non-adjacent if we have the nodes in non-adjacent nodes, right? So let's try to solve that part first. So again, with any tree problem, let's first try to solve this with the smallest tree possible. So let's say this is a tree with 3 nodes. Now we have the ability to half the non-adjacent node. So let's say we half the parent, or we have the 4, so this 4 is now 2, right? Now once we have the parent, we lose the ability to half the children. So we know that we can't have children at all, so we don't need to have them at all, right? So this is the case where we are halving the parent. Now another case is we'll not have the parent. So in that case, we have both the option in the children. Either we can have the children as well, or we will not have the children as well, right? So we have both the option. Now which one to pick? Whatever gives us the minimum value, we'll pick that. Now you might ask that, okay, why we are considering the case where we are actually not halving this? Why would this matter? Now again, this will matter. This will not matter in these 3 nodes, but let's say this node is a representation of some tree. So there is some tree beneath it, and now you remove all the subtree and you replace this entire subtree with a single node where you have two values. One which denote that what is the total path sum or minimum path sum if you have this route, or what is the minimum path sum if you don't have this route. Now as we have seen in previous example that it may happen that it may happen that we will we will pick something which is not half at all. Let's say in this case we are picking this which is half, right? But we are picking this which is not half at all, right? So these kind of scenarios may come, and hence we have to pick the ones which is giving us the minimum value. Mm, whichever either we'll pick the one which in which we are halving this node, or we'll pick the one which in which we are not halving this node, right? So this would be the final mathematical representation of this part. So for this root, we are trying to find two values. What is the value if we, what is the minimum possible path sum if we have this node? What is the minimum possible path sum if we don't have this node? Now, we have seen that if we have this node, we have no other choice and we have to just take the scenario where we are not having the children at all. Now this children is not, is may not be a single children, it may be a representation of a complete subtree, right? So this is what we are doing for with half. So we are halving, sorry, this would be by 2 as well. So we are halving the value of current root, and then we are summing up the value of all the children subtree without halving them, right? And without half, if we don't want to halve the parent, we are taking the value as it is, and then we are for all these children we are taking whichever is the minimum for each of the children, right? Whichever gives you the minimum, we will pick that. And why we are able, like we are able to pick one of them, because we know that we have not halved the root. So because we have fixed that this root is not actually halved, we can actually make the decision independently of each of the children, right? So hope this solution makes sense. So what we are actually doing, just to reiterate, for a given tree, we will first figure out what is the value for each of the leaves. So for this leaf, if we half the node, the value would be 0. If we don't half, the value would be 0, right? Because uh, this is if we do half, right? And this is without doing half, that is complete. So this is 0 comma 0. Similarly, for each node, we can simply find out what is the value. So here it will be 4 comma 8. So if you have it, the value would be 4. If you don't have it, value would be 8. Similarly, if you have it, value would be 3. If you don't have it, value would be 2. Value would be 6, right? Now, once you have figured out the value of all the leaves, for non-leaves, what you can simply do, you can simply apply this particular mathematical formula to get the values for the non-roots. So in this case, what is the value if you have the tree, have the root? If you have the root, you have to take 0 by 2, which is 0, and the sum of non-halves. So you have to take 0 plus 8. So the value would be 8 here, right? Similarly, if you don't have the root, then you can pick the minimum of both from each of these children. So minimum of 0 comma 0, which is 0, minimum of 4 comma 8, which is 4. So you will take 4. So what does this 8 comma 4 represent? It represents that you can forget about this entire tree and replace this tree with one node which have value of 8 comma 4, where 8 is the minimum path sum you are getting after mm, halving the current node, and 4 is the minimum path sum you are getting if you don't have the current node, right? Similarly, you can find the value here. If you have the current node, value would be 2, and you have to take the one which for all the children you have to take the one which is not halved. So 2 plus 8, 10. Now if you don't halve, the value would be 4, and for all the children you can take minimum. So 3 comma 5, 3 comma 8, minimum is 3. So 4 plus 3, 7, right? And finally, for this one, what will the value again? This 10 comma 7 denotes that forget about any subtree below. 10 comma, we have just replaced the entire subtree with a single node which have value 10 comma 7, where 10 denotes the value if you have the current root, and 7 denotes the value if you don't have the current root, right? Now finally, for this, let's say fifth, node number 5, what is the value? Again, if you don't have, or if you halve, the value here would be 6, right? And if you have halved, you have no other choice than to pick the complete value. So 4 plus 7, 11, 11 plus 6, 17. So 17 is the value you will get if you have the current node or current root. If you don't have, the value here will be 12, and you are free to choose the minimum among these two. So 12 plus 4, 16, plus 4 plus 7, 23. So the value would be 23 here, right? So in the same manner, you will fill up all the other nodes, and finally for root node, you will have some x comma y. X denotes what is the total path sum for this entire tree if we have the root, and y denotes what is the total path sum of this entire tree if we don't have the root. And we can just take the minimum of x and y, and that would be our final answer, right? uh, how would the pseudocode look like? Pseudocode would be exactly similar to what we have just discussed. We will iterate over all the children and figure out the cost of all the children first, right? So basically, what we are ensuring through this is that we are first finding out the values for each of the uh, base nodes, right? Once we have figured out that, the value for other nodes would be the formula that we have just discussed before. So without half, if we take, we are free to choose minimum of with or without half from the children, right? If we actually have the current node itself, we are forced to choose without half values of all the children, right? Now after this entire thing ends, each node we will have this pair x comma y, where x denotes what is the value of the entire subtree, if what is the minimum path sum of the entire subtree if we have the current node. Y denotes what is the value if we don't have the current node. And finally, you have to just return the minimum of x and y for the root node, which is 0 in our case, right? So just to reiterate the entire thing, uh, we have to figure out the path sum first. Like we started the problem by figuring out path sum first without actually caring about the scenario where we have to have the node or not. Now, then we saw that, okay, uh, halving node at alternate levels is not the best choice, and we have to do, like we have to do some better thing. And the better thing for would be just to apply some kind of recursive logic for each of the nodes. So each of the nodes would have its own decision whether to have it or not. If you have it, for all the children nodes, you have to take those values where you haven't halved them. If you don't have it, you are free to choose the halved one or the not halved one for all its children, right? Now we have applied this algorithm on a uh, reduced node value, because we replaced each node with its final contribution to the answer. So basically this says that this node 5 would be contributing 12 to the answer. So if we have halved the value of 5, the final contribution of this node would be 6, right? So we build this tree from this given tree by applying this exact same algorithm, where we considered where that there is no concept of halving at all. So once we build this tree, we can simply apply this particular algorithm and get what is the final minimum sum possible. um, if if we have to have some of the nodes, right? So let's look at the code again. Firstly, I would encourage you to pause the video and try to code this entire thing yourself, because we have seen all the pseudocode of all the functions involved in the entire solution. So the code would look something like this. This is just the initialization part. We are initializing some vectors here. After that, we initialized our graph. So we are building an adjacency list. So for each node, we will have a list of all its edges. So for E0, E0 has an edge E1, and similarly E1 also has an edge E0, because the given edges are undirected. Now, after that, we figured out the value of level and parent, right? Now, what is the value of level and parent? We will just do simple DFS as we have discussed. So for each children, the parent of this children would be source or the SRC, and the level of this children would be level of SRC plus one, right? Uh, After this parent and level vector would be completely populated. And finally, what we are doing, we are trying to find for each trip what is the path between u and v, and for each of the path we are incrementing their counts. Now why, like you can just simply not increment the count, or you can simply say, instead of doing this, you can simply say prices of I would be prices of I plus initial price of I. That also you can do. I'm just This is just one of the way to prepare this tree from the given tree. right? So we are just maintaining the count of each of these nodes in all the trips. So for this node, the value would be 2. This comes twice. This node value would be 1. This node value would be 2, and so on and so forth. Now, once you have figured out this for each of these, we just call min cost, and this will populate the two part, half and not half. And finally, we are just taking the minimum of half and not half for the root node, which in our case is 0, because we have rooted the tree at 0, right? Now let's look at the path function. It is again very similar to what we have seen in the pseudocode. Uh, we will first make sure the level is equal. Now we have to make sure first that u is always the one with the highest level. So if the level of u is actually smaller than level of v, we'll just swap them so that this inequality that u's level is always greater is satisfied. Now, once we know that u's level is always greater than equals to v, we can simply make the transitions for u, right? And once level of both of them are equal, we will just simply uh, go to their parent one by one until they actually matches to a single ancestor. So we push u and v and updated u and v to their parents. And finally, because u and v are equal, for that particular node in which they are equal, we haven't considered in this loop, so we are adding it afterwards. So you can also add v here, that would be fine because u and v both are equal. Now this path thing, let's look at the minimum cost finally. Minimum cost, the array we have, instead of having two array in this particular pseudocode, we have seen we have two array with half and without half. Instead of having this, I have just maintained a 2D array where the 0th index denotes the value with half, first index denotes the value without half, right? So we figured out the value for all his children first, and then for the parent we just figured out, like, if we have to do half, we will just half the value of the current node, and for all its children we will just add the cost of not half for all its children. And similarly, for not half of the parent, we are free to choose any of the half and not half from the children, right? So one, like, after you do this for each node, you know what is the value if you have that particular node or if you don't have that particular node. So finally we take the minimum, and that is our answer. So hope this entire solution makes sense. What is the time complexity? Again, this will run in order n. This recursion will also run in order n. The only thing is finding out this path for every trip. So this entire loop will take order n into t time. Now let's say we have to solve a follow-up. The follow-up is you have to solve exact same problem in order n log t or t log n, something of that sort, right? So how will you solve that? Again, encourage you to pause the video right away and try to think that particular problem solution by yourself. So hope you thought about it. Now notice that where from this n square was coming into picture. uh, the reason for order n of path is that we are trying to find all the nodes in this range, and then we are also uh, updating their counts, right? Now if we have to reduce this order n into t into some of something of n log t or t log n, we need to figure out two things. Firstly, we need to figure out the LCA of two nodes efficiently, right? So this is the first part. We have to figure out the LCA efficiently in order log n time. And second, let's say we figured out LCA. So we know that the path can be divided into two parts. One, add everything to this particular thing, and then add everything to this particular thing. So basically add one to all these nodes and add one to all these nodes. So this is the second operation, add one to everything in the ancestor of u till LCA, right? So we have to come up with some algorithm that will help us understand or answer these two queries in log n time itself. Now For the first one, figuring out LCA in login time, this is a standard problem, and we can solve this with binary lifting easily. I have explained the entire concept in one other video. I would link that in the description down below or somewhere in the top right eye section. You can watch that as well. This that algorithm would help you figure out the LCA of two nodes in order login time. So now we know what is the LCA. So for 6 and like let's say for 6 and 8, we have to find out the LCA, which is 5. We will able to add, we will be able to get 5 in order login time itself. Now once you get 5, you need to add 1. Basically we were incrementing the count here, right? So we have to add 1 to all these nodes, like starting from 6 to all its ancestor up till 5, and also add 1 from to all the nodes starting from 8 to all its ancestor up to 5, or just below 5. Now how will you do that? Again, encourage you to pause the video and try to think first by yourself. So the problem is very similar to the prefix sum approach. So here you can think of this entire thing as an array, right? So let's just get rid of this. Uh, so just think of this entire part as an array, right? And let's say you are asked to add one in this particular subarray. So what you will do, you can simply add 1 here and subtract 1 from here, and then take a prefix sum. And once you take the prefix sum, you will see this 1 would be propagated all the way to 5, but not 0, right? Because you have already subtracted 1 from here. So you can just think of this entire uh, ancestor of a particular node as an array, and just add 1 to the first node and subtract 1 from the last node. So let's take some example. Let's say we have to do this for 8 and 9. So for 8 and 9, we can just first call the LCA. We will get the LCA of 8 and 9 as 5. So what we will do, we will simply add 1 to all the nodes starting from 9 all the way up to 5, but not from 0. So we'll add 1 here. So we'll add 1 here and subtract 1 from here, right? And similarly, let's say you have to add everything, or add 1 to everything in this range. So what you will do, you will add 1 to this node and subtract 1 from this node. So that's what we have done. Subtract 1 from this node and add 1 from this node. So this would, once you have done this, you you can do this for all the paths. So let's say after doing all the paths, the current structure looks like this. So what does this mean? It means that 1 would be added to this part, this part, this part, and this part. Now how would you make this happen? Again, you can simply see that what is the total contribution at this node. Total contribution at this node is the sum of the entire subtree, right? Basically, every node here would contribute to this node, right? So that's where the contribution of this node would be the sum of the entire subtree. And finding out the sum of entire subtree can again be solved using a simple DFS. So what we have to do, for each node, we have to find out what is the sum of the entire subtree, and that would be the final count of this node. And to do that, we can simply use a DFS. The DFS would be simple: just iterate over all the children, figure out the value for the children's first. Once you figure out the value for the children, you can just add it to the current node, and that would be the value for the current node. So hope this entire solution also makes sense. I am not showing you the exact code for this. But I would strongly encourage you to try to code this solution by yourself and try to get it submitted in the same problem, because here we are just trying to reduce the time complexity. So you can use the same problem and submit your code in the same problem. If you face any difficulty, you can post them in the comment section below, and I would be happy to help. So that's it. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.